Well, hello, my name is Chris Parkin, and I want to welcome you to the William W. Hay Railroad Engineering Seminar. And before I introduce our speaker, I'd like to take care of a couple of housekeeping items. First of all, if you have a cell phone, and who doesn't these days, please turn it off or turn it on to vibrate. If we have a fire alarm, we should exit from doors on either side of this room. And can you hear me? Is this coming through? Okay. We now have stairs and exits at both sides, so you can take them either one, and then we'll exit on the first floor outside to Main Street, and we'll gather by the Hydro Systems Lab. We'll use the buddy system, so please note who's next to you and make sure that they get out. And if we have severe weather, we don't want to go outside. Instead, we'll exit again from either this door or that door and go back down the hallway behind that wall into the old part of Newmark Lab and then down to the basement. Again, a very safe refuge. If you didn't swipe your ID card when you checked in, please sign the attendance sheet that we'll pass around.
Thank you.
And if you did not receive a direct email announcement for the seminar but would like to in the future, please include your email address. I can't turn pages with this going. I'll ask the speaker if the speaker could please repeat questions from the audience if we don't get a microphone to them, so that the people who are tuned in can. Okay. So I guess we're ready to go. And I'm going to have to ask you for some numbers because I didn't get them from you ahead of time. So the William W. Hay Railroad Seminar Series is sponsored by the Rail Transportation and Engineering Center here at the University of Illinois at Urbana-Champaign. And on behalf of all of us, we thank AAR, BNSF, CN, Hanson Professional Services, and Union Pacific Railroad for their ongoing support of RailTech. It's greatly appreciated by those of us here on campus, as well as those of you participating via the internet. So we'd also like to welcome those people. We have more than how many? 170 people joining us who registered for the seminar, and they're from how many countries? Don't know that yet. So anyway, we often have people from multiple countries and multiple continents, so we welcome all of you. And the list of attendees includes freight and passenger railroads, transit organizations, federal and state DOTs, engineering firms, universities, research organizations, technology developers and suppliers, and others. And we're very pleased that you could join us. Those of you who wish to receive PDHs for your participation, please send us an email at heyseminar@illinois.edu with your information as described in the email announcement for the seminar. So to introduce our speaker and what he's going to be talking about. A critical aspect of safe railroad freight transportation in North America is the extensive set of freight car mechanical standards managed by the Association of American Railroads, or AAR. These standards are in a continuous state of refinement and improvement by the AAR mechanical committees that include representation from railroads, car builders, car owners, and in some cases, regulatory agencies. These standards enable efficient, unrestricted interchange of the 1.5 million freight cars on railroads that operate in the United States, Canada, and Mexico. This presentation is going to discuss key aspects of the history, development, advantages, and disadvantages of AAR and interchange rules and how exceptions are handled. Our speaker today is exceptionally well qualified to discuss this subject. Mr. Richard Dawson has a long and successful career in the railroad industry, serving in railcar structural design, manufacturing, and engineering management roles. He completed his BS in mechanical engineering at the University of Rochester in 1963 and took his first rail industry job a few years later with the New York Central Railroad as an assistant engineer. He rose to positions of increasing responsibility, designing, developing specifications for, and managing the New York Central and its successor, Penn Central's 160,000 freight car fleet. In 1973, he moved to Trailer Train Company, where he was a research engineer and manager of boxcar engineering, and his work there included developing specifications for their new rail box fleet that ultimately grew to 20,000 cars. In 1977, he moved to Berwick Forge and Fabrication, fabricating, where he rose to the level of vice president freight car engineering and had principal responsibility for their freight car engineering and management functions. In 1984, he returned to TTX, the successor to Trailer Train, where he continued rising through positions of increasing responsibility, ultimately becoming their chief engineer of new car engineering. Mr. Dawson retired from TTX in 2003, but since then has remained quite active in the field as a consulting engineer, assisting clients on railcar engineering projects. He's been a member of numerous AAR task forces and committees, including serving as the chair of the Equipment Engineering Committee of the AAR. And he's a licensed professional engineer, has 9 patents and 8 publications, including the 2-volume book, The TTX Story. I'm very pleased to introduce Mr. Dick Dawson, who will present his seminar entitled Managing the Interchange of Freight Cars Among North American Railroads.
Thank you, Chris. How many businesses can you think of in which your competitor can inspect your equipment, which may cost up to $100,000 or more, can decide based on his inspection that your equipment needs to be repaired, can perform that repair, and send you a bill for that repair, which is the first time that you hear about it, and you're obligated to pay the bill? Well, that is the case in the railroad industry, specifically relating to the interchange of freight cars. And that's what I want to talk about today. So I'm going to be talking about the origin of the freight car interchange system in North America, the benefits of interchange, but there's also a disadvantage, as we'll see. I'm going to talk about the AAR interchange rules, which are the mechanism through which cars are exchanged between railroads and car owners, and also on how, on how exceptions to the interchange rules are handled. So before the introduction of railroads, heavy cargo, for all practical purposes, could only travel long distances by water, either by canals, rivers, or ocean voyages. The roads that were in existence at the time, and there were not many of them between towns or cities, were totally inadequate for handling heavy cargo. And with the considering that the transport of heavy goods relied on water transport, prior to 1825, grain and other products produced in what we now call the Midwest, was then called the West, that was going to move to the east, had to first travel by river to New Orleans, where it would be transshipped to an ocean-going ship, and then carried to the port on the East Coast that it was intended to. After the introduction of the Erie Canal in 1825, that distance was shortened considerably so that goods could travel across the Great Lakes to Buffalo, New York, take the Erie Canal east to the Hudson River around Albany, and then continue on south to New York City. This was one of the major reasons why New York City, for example, surpassed Philadelphia, Boston, and Charleston, South Carolina, because of this ability to receive cargoes much less expensively. So this water system worked reasonably well, but it had a number of disadvantages, including, of course, freezing in the winter, which we're all accustomed to here in central and northern Illinois. You can't move goods across the Erie Canal for several months of the year, and so that meant that people who were receiving goods had to stock up before winter came and the navigation system was over. This still exists for example, in iron ore traffic on the Great Lakes. The first railroads were very short, and they were, in many cases, established by cities with the objective of hauling freight to individual cities for local consumption of the goods or transfer to water carriage to go somewhere else. We think today of railroads as being primarily oriented towards hauling freight, and for the vast majority of the North American railroad system, moving freight has been the major function of railroads. However, in its first few years before freight transportation really started to take off, many of these early railroads actually carried more passengers than freight. And I was tempted to include in this bullet point here that the first railroads were intended to haul freight and passengers to individual cities for local consumption. But then I realized that when we're talking about hauling passengers for local consumption, it doesn't exactly sound something that we want to go into, so I left it out. Moving right along, railroads, another characteristic of those very early railroads was that railroads meeting at one location were often not connected. And so consequently, if goods were going to be moved from a railroad arriving at one side of a town or city and was then going to continue its voyage on another railroad, they would have to be unloaded from the first railroad's freight car, hauled a short distance, probably in wagons or something along that line, and then reloaded into the second railroad's car. This system was called breaking bulk. Needless to say, this process of breaking bulk was expensive, it wasted time, and it risked damage or pilferage to the goods being handled. So the obvious solution to this problem is, instead of breaking bulk, just transfer loaded cars from the first railroad to the second railroad. And while that's an obvious solution, accomplishing it was not so obvious. There were a number of impediments to being able to do this. For starters, all of these separate railroads that were created independently chose their own track gauge. And there were a variety of different track gauges used in the United States. This is a problem which I'll see that was eventually resolved here, but continues to create problems in countries like India and Australia, where a number of the different railroads operate on different track gauges. In 1861, 53% of the track in the United States used a 4-foot 8.5-inch gauge. That's the distance between the inside of the railheads. This is called standard gauge, and it originated with George and Robert Stephenson with the first railroads in England. But if 53% were built to standard gauge, that meant 47% had different gauges, which ranged anywhere from 4-foot 9 inches to 6-foot 0. But even if the track was at the same gauge, there were still some potential problems in moving freight cars from one railroad to another. The couplers used to connect one freight car to another and to the locomotive were not necessarily of a compatible design that they could be connected to each other. And even if the couplers on two different freight cars were of the same basic design, they may have been located at different heights. And then once, aside from that physical limitation of track gauge and coupler connectivity, there was the issue of how to track foreign cars not belonging to the railroad on which they're running at the time. How does the car owner get paid for the use of his car? If somewhere along the line, when it's on a different railroad, the car needs repairs, how is that going to be handled? Is the car owner who's going to pay for the repair? Do you need to get the car owner's approval to repair it? Do you, there are just a number of issues that result from that. This issue of incompatible track gauge really came to a head during the Civil War, when a great deal of both troops and material and supplies were shipped on routes which previously had not seen a great deal of traffic, but had to be to support the armies in the field. And the fact that track gauges were incompatible in many cases really complicated that getting the material moved. One of the responses to this difficulty with car interchange was the establishment of private car lines. And in the railroad industry, a private car means a car not owned by a railroad company. So these private car lines were established to provide cars for interline shipments over specified routes. Once the railroads themselves got the interchange issue relatively well established, many of these private car lines were absorbed by operating railroads, but private car lines continued to be the norm for many years for refrigerator cars and tank cars. The gauge issue started to be resolved around 1870, when many railroads built to other gauges started to convert their track to standard gauge. The southern railroads, those south of the Ohio River and Mason-Dixon line and east of the Mississippi Railroad, were almost all built to a 5-foot 0-inch gauge, but they too ended up converting to standard gauge. And on June 1, 1886, throughout the South, on every section of track, one rail was moved over 3.5 inches to bring the track to standard gauge. This raises the issue of how did they also accommodate the difference in gauge in terms of the spacing of the wheels on their cars and locomotives. And frankly, I'm not really sure how that was accomplished, but clearly it had to be. A major development in establishing the freight car interchange system was the formation of the Master Car Builders Association in September of 1867, whose objective was to formulate rules and procedures to handle repairs to foreign cars and to develop standards to make cars compatible. So the Master Car Builders Association was comprised essentially of representatives of railroads who were responsible for the building and also the operation and maintenance of their freight cars. The Master Car Builders Association eventually evolved into what is now the Safety and Operations Division of the Association of American Railroads. And over the past 154 years, the Master Car Builders Association and the AAR have established a series of standards to make components interchangeable, thereby simplifying repairs, and to ensure that the car and its components have strength adequate for the railroad operating environment, which is frequently not too gentle. Among the standards that they established was coupler height. At the time that the MCB was formed, virtually all freight cars used some variation on the link and pin coupler system. standards were established for that. And then later, when knuckle couplers were introduced, the MCB established standards for them. It also established a series of axle sizes, each of which would have different weight capacities, so that there was the limited number of axle sizes and configurations rather than whatever a car builder happened to think was appropriate. They established standards for the journal bearings, which supported the car on the axles, and journal boxes, which contained the journal on the axle, the bearing, and also provided a means for lubricating the axle. The early freight cars were equipped with handbrakes only, but eventually the adoption of air brakes became mandatory, and the MCB and the AAR have established standards for the components of the air brake system, brake cylinders, brake shoes, air brake control valves, and so forth, and for the performance of the brake system. So here we have three different coupler systems. So at the left here, we have, am I working this right? All right, at the left we have the link and pin system. So this is the coupler on one end of one car. To the right, of course, would be another car with the same type of system, and it also would have a vertical pin that would extend down through the end of the loop. Notice that all of the car body, the portions of the car body that we can see into which the coupling system is installed, are of wood. To the right, we have among the first knuckle couplers. This is the Janney Coupler, which was invented by a man named Eli Janney. And so now the significance of this system is that when the knuckle on one or both of the facing couplers are opened and the cars are brought together, the couplers will couple automatically with no need for a brakeman to get in between the cars and insert the pin. And similarly, by operating the handle on the uncoupling lever as seen here, cars can be uncoupled without the need for a man to get between the cars. Down below here, we have a modern freight car coupler and its attachment system. Note that now all of the adjacent car structure is of steel. You'll notice that in the illustration of the Janney coupler, the freight car underframe is still of wood construction. So it may seem pretty obvious that there are a number of benefits to being able to interchange freight cars from one railroad to another. It eliminates the need to break bulk wherever different railroads meet, and the interchange system as administered by the AAR ensures that all cars in a train have compatible braking and coupling systems. It ensures that cars have an acceptable level of support, acceptable level of strength rather, to support their load and to survive the railroad environment. And it has established a common system to repair cars and to bill both for the use of foreign freight cars and for their repair. So those are all advantages, but there is in fact a disadvantage to it, which is that any improvements to systems or components which are not compatible with the existing equipment are very difficult to implement. The use of air brakes and knuckle couplers ended up having to be forced on the railroad industry by the federal government in the 1890s and 1900s. Both air brake systems and knuckle couplers had been in existence by 1880 or so, and a number of railroads incorporated some of that equipment in their cars, but no one was able to find a way to accomplish changing all of the brake systems and all of the coupling systems on the approximately 1 million freight cars that were in operation in the United States in 1900. But once this was accomplished, the use of air brakes and of the knuckle coupler made it feasible to haul much heavier and much longer freight trains. And in this respect, the United States railroad practice started to diverge from the rest of the world, most of which continued for many years to use hook-type coupling systems and either vacuum brakes, which are much less effective on longer trains than air brakes, or in some cases, as in England, for many years, freight cars had no brakes at all. What we call a caboose in England was called a brake van, and the reason for that was because it had brakes, and the brakeman applied brakes on the brake van. The locomotive engineer would apply brakes on the locomotives, and the ability to slow the train down and stop it relied solely on the action at the two ends of the train, with the freight cars themselves contributing no braking effort. Obviously, this significantly limited the length of freight trains that were possible. Here we have a fellow who's having a pretty rough night. And this picture may be, I'm not sure I would want to use the word exaggerated, but it is certainly there to create the impression of a very difficult life of this brakeman. And in fact, it's not far from the truth. When freight cars only had handbrakes to retard their motion, a brakeman, and that's why they're called brakemen, in the caboose would get out, climb up onto the roof of the adjacent car on the running board, and move from car to car, operating the handbrakes to apply the brakes on those cars. If you had a train of any length, realistically, he was not going to be able to get to every car. The amount of force that he applied to the handbrake wheel would vary. It might not be enough to significantly retard the train. On the other hand, if it was too much, it might slide the wheels. And yes, trains did operate in the middle of February in Minnesota and across the northern United States, where the weather was often pretty nasty and cold, and they operated in all hours of the day, and brakemen did have to get up on the cars to apply the brakes. So I want to talk now about the Aar Interchange Rules, which are the mechanism through which the North American railroad industry manages the movement of cars between railroads. The interchange rules are maintained and revised as necessary by technical committees of the AAR. As Chris mentioned, I was a member and chairman of the AAR Equipment Engineering Committee. Chris is a member of several AAR technical committees. The committee members represent railroads, private car owners, car and component manufacturers, and shippers, and occasionally representatives of regulatory agencies. All freight railroads and the owners of interchange freight cars must subscribe to and be governed by the interchange rules. Now, I should mention that there is another set of standards that apply to freight cars, the FRA Freight Car Safety Standards. These are based on the AAR interchange rules, but they are a much smaller portion of the interchange rules. They concentrate solely on the safety of equipment as opposed to interchangeability or paying for repairs or whatever. It is of significance, however, that while the AAR interchange rules, strictly speaking, apply only to cars that are interchanged between railroads, the FRA freight car safety standards apply to all cars on all operating railroads. So let's look at the basic principles on which the interchange rules are based. First, railroads are responsible for the condition of all cars on their lines at all times. If a foreign car causes a derailment because it had a significant defect, let's say in the coupler, the operating railroad can say, oh, gee, I'm sorry, it's not my fault. It was that other guy's car. It was in really terrible shape. Does not work. Once he accepts the car, he is responsible for its condition. If in fact the car had a defective coupler when he accepted the car, it is then up to him to fix it or accept the consequences of anything that is caused by that defect. Car owners are responsible for and are chargeable with repairs performed on their cars caused by ordinary wear and tear in fair service. The handling line, which is to say the railroad on which the car is located at the moment, is responsible for damage caused by unfair usage. I think it's fair to say that this would be considered unfair usage. This derailment occurred on the Pennsylvania Railroad in the early 1960s, and needless to say, it was responsible for the damage caused to all of these cars, or for that matter, to the lading that may have been on the cars. And if some of these cars were damaged beyond repair, which is entirely possible, then the handling line is responsible to pay the car owner the depreciated value of the car. And there is a standard system for determining what the depreciated value is. So again, continuing with the basic principles of the interchange rules, many of the individual rules require compliance with other AAR standards and specifications. And so this is how those other standards and specifications are enforced. Railroads must accept cars offered in interchange that comply with the interchange rules and its reference standards, but they can refuse to accept cars that do not comply. So this right here is the basic enforcement mechanism of the interchange rules. Your car doesn't comply with the rules, I'm not going to accept it. If we look at the structure of the individual rules in the interchange rules field manual, and I should mention that the interchange rules are published in two separate manuals. One is the field manual, which governs the inspection and repair of cars in the field. The other is the office manual, which includes a number of items such as the cost established to perform repairs, allowable life of cars, and whatever. Many of the rules in the field manual are arranged to apply to a specific component of a car, a coupler, the air brake system, whatever. So if in an individual rule, the first section is section A, is wear limits, gauging, cause for renewal. When are repairs necessary? If you go out and if you look at a coupler on a car, is this satisfactory or not? This determines what is a necessary cause for engagement. If we go back to my comment at the very beginning about your competitor inspecting your equipment and deciding whether or not it needs to be repaired, Section A of the appropriate rule in the field manual is what governs whether or not repairs are necessary. Section B, correct repairs. If repairs of some sort are needed, what repairs are acceptable, what repairs must be made. Recondition requirements. In some cases, components that are applied to a car can be new, they can be secondhand, or they can be reconditioned. And if they can be reconditioned, this section will refer you to the appropriate standard for reconditioning that component. Section D is welding requirements. The first question is any welding on that component permitted? Welding is absolutely not permitted on wheels and axles, for example. If weld repair or buildup by weld is permitted, what requirements must that repair welding conform to? And then general information includes just a variety of other information that clarifies repairs to that particular component. And then the part that makes the accountants happy, the billing repair data requirements, the information that must be provided to the car owner in a repair bill. If a wheel, for example, is determined to be unacceptable for one reason or another, you have to identify which wheel on the car it is. Why is it unacceptable? What repairs were made? What was applied to take the place of the one that was removed? All right, so I've already mentioned the office manual of the interchange rules, and it includes the costs that are to be charged for the labor to perform a repair. And most common repair items have a standard number of repair hours that are to be used in repairing it. It doesn't matter whether you have a very efficient shop or one that sort of just barely skates by. If you are going to replace a coupler knuckle, for example, you can charge, and I'm making this figure up, 0.127 hours to replace that knuckle. Regardless of whether you did it in less time or more, you charge the standard hours. And those standard hours are determined, again, by technical committees of the AAR. In this case, the Car Repair Billing Committee. There is a standard hourly wage rate, which is adjusted annually. So you know how many hours you can charge to perform that repair. You know the hourly wage rate, so multiplying the two together tells you the labor charge to perform that repair. And there are standard values applied for material used in the repair. For most material used in repairs, like wheels, couplers, fasteners, brake shoes, and on, there are standard costs for new material, secondhand material, which is material that has been used before but is acceptable for application in a circumstance like this, and for reconditioned material. So here is an excerpt from what is probably the longest rule in the field manual, Rule 41 for wheels. And it's probably appropriate that Rule 41 is the longest rule because for most freight cars, wheels are the largest maintenance cost for the cars. Here we're showing the application of a standard gauge, which every repair shop must have, along with a number of other specified standard gauges, which is being used to check whether or not the wheel flange is too thin. Wheel flanges will typically wear on the side that faces the gauge face of the railhead. If the flange gets to be too thin, then it is prone to picking switches, which is to say it will go between one of the movable points of the switch and the adjacent stock rail, which will then lead to trouble and very possibly a derailment if they're moving at any particular speed. The maximum, or I should say the minimum allowable thickness of a wheel flange is 15/16 of an inch. And if you apply this gauge and start to push it down, obviously the thickness of the gauge is not, of the flange rather, is not constant, it tapers. If you're able to push it down to the point that am I not getting it here? Pardon me? Oh, that's cheating, Chris. God's sake. So if you can bring this gauge down far enough that this point contacts the wheel tread, the wheel has failed the gauge and it therefore needs to be replaced. If you apply the gauge and start pushing it down, but it stops before this point matches here, then the flange contour is acceptable. So this is just an example of many other typical means that are used to determine whether or not a component is acceptable. Most of the repair work performed at freight car repair tracks under the interchange rules relates to different components of the car. If a component is found to need repair or reconditioning, that is usually not performed at the car repair shop. Typically, the component that is found to be defective will be exchanged, that the shop has on hand, and the removed component, if in fact it can be repaired or reconditioned as opposed to being scrapped, will be sent to another shop that specializes in reconditioning those components. Thus, you have wheel and axle shops, which concentrate on repair work on wheels, axles, and the application of roller bearings. You have shops that concentrate on reconditioning air brake valves and so forth. And so the car owner is charged for the difference in value between the removed component and the component that was applied. So let's take as an example, a CSX freight car is on the Norfolk Southern Railway. A car inspector in the yard looks at this CSX car and sees that one of the coupler knuckles is cracked. So the car gets sent to the repair track. The Norfolk Southern replaces the knuckle and sends a repair bill to CSX. And so the charge works out as follows. So in this case, we'll say that they applied a new coupler knuckle. Well, the value, and this is from like the field manual, the interchange rules from say 2 years ago, the value of a new coupler knuckle is $135.35. You're not allowed to repair cracked coupler knuckles. So its sole value is as scrap, but NS is not going to send the knuckle back to CSX to collect the scrap on it. They will scrap it themselves, and they will deduct $8.69 from the repair bill sent to CSX. And again, both of those values are standard values worked out by the Car Repair Billing Committee. And then finally, the labor charge to change out the coupler knuckles is $16.51, which again is a combination of a specified number of hours and a specified hourly labor rate. So CSX gets billed $143.17, and they have to pay the bill. The bill is not sent directly to CSX by NS, but rather it is sent through the AAR, which serves as a clearinghouse for repair bills. They receive the repair bills from the repairing facilities and send them on to the car owner or whoever is responsible for the cost of the repair. And the net difference in billing between two railroads is paid monthly. Let's say that for the month of August of this year, Norfolk Southern charged CSX $500,000 for freight car repairs. CSX conversely charged Norfolk Southern $400,000 for repairs. What will end up is that CSX will pay Norfolk Southern $100,000. You don't have $500,000 and $400,000 checks crossing in the mail. The AAR Mechanical Inspection Division periodically audits repair shops to ensure that they are performing repair procedures in accordance with the interchange rules and the various component specifications and standards, and that they are billing accurately. Now, it's important to note that the interchange rules do not prevent railroads and car owners from reaching agreement among themselves to operate equipment that does not comply with all AAR standards, or for that matter, to charge different amounts for repairs. And one example of that is that for those of you who may be familiar with articulated double stack cars, the trucks at the articulated connections are nominal 125-ton trucks. These trucks are not approved for unrestricted interchange because of their relatively high wheel loading, but most railroads agree to handle them based on satisfactory performance in service. If a car owner receives a repair bill that he believes is improper, he can appeal to the Arbitration and Rules Committee, which both establishes the interchange rules and also arbitrates differences between parties over them. And all signatories to the interchange agreement agree to accept arbitration rulings as final. And if the AAR finds that a railroad has been submitting fraudulent repair bills, they can require that that railroad forfeit all billing from that shop, or even the entire railroad if this practice is widespread, for some period of time. This is a pretty heavy rap in the knuckles, and which serves to keep the repair billing honest. My former employer, the Penn Central Railroad, in fact, was hit with just such a charge some time ago because of fraudulent repair billing that was being performed out of their shop in Altoona, Pennsylvania. Here we have an articulated double stack car with the 125-ton truck between the two car bodies. Note that it is marked 125T to indicate to railroads handling the car that it has 125-ton trucks. This is, including those markings, is not required by the AAR, but we started doing that at my employer, TTX company, and I noticed that most other owners of articulated double stack cars do so as well. So, what have we discussed today? Railroads enabled heavy cargo to be moved efficiently over routes where water transport was not feasible. And in fact, most canals were replaced by railroads. So some of them, the Erie Canal, for example, which was one of the few American canals that was actually a commercial success, eventually had to give up freight traffic because they could not compete with the New York Central Railroad that ran parallel to it and now operates basically for handling pleasure travel. There is, however, still some barge shipment on rivers and a few canals over some routes. Transportation by rail would be hopelessly inefficient if railroads could not exchange freight cars regardless of owner. And that interchange of freight cars started to expand significantly shortly after the Civil War, as the United States was entering into the Industrial Revolution. And as a consequence, manufacturing and transportation of goods expanded explosively. Standards and procedures established by the Master Car Builders Association and later the AAR made interchange possible on a large scale. And the AAR interchange rules are the basis of freight car interchange in North America. So I thank you for your attention and would be happy to answer questions if we have time for some.
We have some questions here.
So this has been my observation, but maybe you can help me confirm, but has there been an increase in private car ownership and then decrease in railroad car ownership in terms of the overall car fleet?
Yes, there has. Currently, somewhere between a half and 2/3 of all the freight cars operating in North America are owned by private car owners. Like my former employer, TTX company, there are a number of leasing companies which provide cars. When the Powder River Basin in Wyoming started shipping large amounts of coal to electric utilities, almost the considerable majority of the electric utilities bought their own freight cars. So the railroads essentially have chosen to let other people own a large number of the freight cars themselves, while they concentrate their investments on track, bridges, equipment, which is much more difficult to get other people to finance.
So earlier in your example about talking about accepting a car in interchange.
Yes.
And the railroad, some of the liability as soon as you accept the car.
Could you speak a little louder, or I'm not sure that, or is the microphone on?
At what point does the accepting a car and interchange occur as soon as it enters your track owned by that
Exactly.
railroad, or
Exactly.
so even if you don't have a chance to inspect it beforehand?
Well, if you don't inspect it, then you have by default accepted the car as is. Typically, when cars move from one railroad to another, they will pass through a yard, and the receiving railroad will have car inspectors on hand who will inspect the cars as they come through.
Follow-on question, does that reset the 1,000-mile inspection requirement? If that's still, how does that work? As soon as you hand over to another railroad,
Yes.
they keep track of where the last major inspection was?
No, in effect, they don't care when the car was last inspected before they get it. The whole, the key element there is that once they receive the car, once they accept it, they are responsible for it. So it's up to them to inspect the condition of the car at that point.
Great presentation.
Thank you.
In addition to the first question, with the increasing number of cars being owned by private companies, the operation of like looking if there's a defect in a car by the railroads, it's becoming more profitable.
I'm not sure that I understand the question. The railroads are usually happy to let another company invest the capital required to purchase the car. They are relying on the fact that even though that private car owner is not going to operate the cars and is maybe somewhat less sensitive to issues of safety and reliability, let's say that the railroad is, but they're going to rely on the fact that that car must conform to the applicable AAR standards for that car. And so consequently, through their participation in AAR technical committees, the railroads want to ensure that all cars that are going to be offered to them will meet some minimum standard of strength and safety.
We have a bunch of questions coming in online as well, but
does the AAR have like a geographical like offset? Because if say you had to repair a car in California, it'd probably be a lot more expensive in terms of materials and wages than Wyoming, or does it not?
Too bad. The Car Repair Billing Committee establishes an hourly rate that is felt to be reasonable for the entire United States. In fact, some railroads may have to pay higher wage rates than do others, but the hourly rate is uniform across the entire country. Now this, and it's also based on the efficiency, so that's the hourly rate. And then in terms of the number of hours to perform a particular repair, let's say, for example, that you need to that a coupler yoke, which is one of the pieces by which a coupler is connected to the freight car. Let's say that a coupler yoke is found to be cracked and needs to be removed. Well, to remove that yoke, you've got to jack the car up, you've got to drop a number of support plates, take the coupler and draft gear and yoke down, separate them, put a new coupler in. So all of those different operations are looked at, and times are established for each one of them, through time and motion studies. And those and the number of hours that are set are based on a typical repair facility, not necessarily the most efficient repair shop in the world, but not necessarily a small mom and pop operation either. And so I've never been to a car repair billing committee meeting, but I can imagine that there are frequently some lively discussions over what is an appropriate number of hours to perform particular repair tasks. Now, one of the consequences of that is that if you have a super duper efficient wheel shop, for example, then you can do this work at significantly less time than the AAR hourly standard. And so if you get paid the hourly rate, boy, you can be making some pretty good money on that. And as a consequence of that, repair shops are set up to perform this work, which they will then negotiate with car owners to say, and a classic example of this was the Chicago and Northwestern shop in Clinton, Iowa, which was a really effective wheel shop, was relatively close to Proviso Yard, just west of Chicago on the CNNW. And so any wheel work that was found to be necessary at Proviso was sent to Clinton. This was a big moneymaker for the CNNW, but they also arranged with some companies like my former employer, TTX company, to have wheel work sent to their shop there, because they would be willing on a contract basis to do it for somewhat less than the AAR rate, but still at a rate that made money for them.
Internet is brimming with questions. So let's give them a chance. So the first one is, and you touched on it a little bit, but what's the maximum specified limit for freight car life in a freight car interchange system in North America?
It's, with one exception, it's 50 years. At one time, there was no maximum freight car life, at least so far as I can tell. But around 1970, the AAR, and this was also around the time that the FRA freight car standards were applied. The FRA freight car standard maximum life is 50 years, period. At about the same time, 1970, or it might have been 71, the AAR also established a 50-year maximum life, but it was going to be reduced by 1 year for every succeeding year until it came down to 40. And so there was a period of time in which the AAR said that a freight car can operate for no more than 40 years since the date built or originally built. The FRA said you can't operate more than 50 years since it was originally built, period. So consequently, if you went through a rebuilding process, and again, the AAR established a number of standards of what you had to do to a car for it to be considered rebuilt, you could get that extra 10 years. But after an increase in the design loads that are required when conducting stress analyses of freight cars, after those design loads were increased in 1974, and the railroad industry was noticing that cars built more recently seemed to be holding up very well after 40 years, the AAR agreed to allow cars built on or after July, I believe it was, of 1974 to operate for 50 years. And so any car that would have been 40 years old in 1974 is long since gone. So for all practical purposes, the limit is 50 years. But I said there was an exception to that, and that is that cars that go through another process called increased life status, which has some very stringent requirements for inspection, updating of components and whatever, those cars can operate for 65 years of life. The way it's actually worded, it's 40 years since receiving your increased life status, but no more than 65 years.
Okay. Next question is from an old friend of yours. Can you comment on defects that are not easily seen by conventional inspection methods, such as something in the center bowl hidden from view? What's the process for dealing with these latent type defects?
Yes, that is a nasty issue, and realistically, when a freight car is offered from one railroad to another, the receiving railroad is not going to jack the car up and inspect the center bowl. And so if the condition of the center bowl doesn't manifest itself in some other means, such as a restriction to truck swivel or whatever, it probably will not be caught. But if it is found, it will probably be owner's responsibility.
Okay. Next question is, what about cars that handle steel coils? Are they also interchanged?
Yes, absolutely. There may be, so long, unless they're going to operate within the confines of a steel mill or operate entirely on one railroad, then they will be subject to interchange and therefore subject to the interchange rules. Once they are on the transportation tracks, I'm going to use a term here, of a railroad, they are responsible to comply with the FRA freight car safety standards. So the only way that a coil steel car, including hot coil cars, by the way, which as it happens, I have a certain amount of experience with, they are handled the same as any other interchange car.
Okay. Next question is, are there exceptions to these sets of rules for freight car interchange, such as for hazmat cars?
I would say not so much exceptions as it is that there are additional requirements that hazmat cars must comply with.
Okay. In other fields, the standards development process includes both equipment manufacturers and users. Are you able to comment on, one, how well freight car manufacturers and railroads cooperate to set the standards, and two, any tensions between car builders and the railroads in that process?
In the old days, which I understand has different meanings to many different people, but let's say prior to about 20 years ago, the AAR technical committees consisted almost entirely of railroad employees. My former employer, TTX Company, originally named Trailer Train Company, was kind of a special case since it was owned by the nation's major railroads. And consequently, even though strictly speaking, it was a private car line, it was, many of its employees were authorized to sit in technical committees. That was briefly rescinded at one point, but by the mid 1990s, let's say, as it was becoming apparent that large portions and eventually the majority of freight cars were owned by other private car owners, the AAR started to accept private car owners on their technical committees. And shortly after that, freight car manufacturers and some component manufacturers. I believe that the tank car committee, of which you can certainly speak to better than I, had a broader membership much earlier than that. But the way it works now, that most of the AAR technical committees include railroad members, and incidentally, one of the decisions was was that railroad members will always have a voting majority on all technical committees. And you might be inclined to say, hey, that's not fair. There are more our cars than yours. And the response to that is, we're the ones who have to bear the brunt if a derailment occurs. We're financially liable for the derailment, to say nothing of the fact that it messes up our whole transportation operation, puts our employees at risk. And so while, yes, we very much appreciate the input from other industries, we have to retain control. And I think that's a perfectly reasonable stance to take. And so, yes, there will inevitably be some differences of opinion between operating railroads and manufacturers or private car owners, but from my experience, it works remarkably well.
Yep, I would agree with that from my tank car committee experience. And you're right, voting majority by railroads on the tank car committee, but there's also a contingent of shipper organizations representing the different products that tank cars transport, as well as the car builders and car owners.
Right. There are not shipper representatives on most AAR technical committees. But as you say, there have been traditionally on the tank car committee for many years. The AAR Safety Appliance Task Force, which I ran for a number of years, also had representatives of shippers. We also had representatives of railroad labor organizations, which is not at all typical of AAR committees. But in this case, since we were dealing with safety appliances, we felt that it was necessary to have them participate.
And I'll just add one more thing about the tank car committee. The tank car committee in general does not concern itself with the running gear. It's concerned with the tank and appurtenances associated with the particular products.
Yep.
And there's a liaison with the equipment engineering committee for all of those other matters, of course. So, all right, another question from the internet. How much does inspecting foreign cars add to the dwell time that a car in an incoming yard?
I don't have a good feel for that. You may be looking at, a couple hours, maybe something along that line. Now, and realistically, a yard at which cars are received from other railroads or from other car owners will frequently also be one in which other routes of that same railroad come in. And so it's worthwhile for the railroad to inspect its own cars there at the same time. typically in a transportation yard, the car inspectors are going to look at all the cars on a particular track, not just foreign cars or cars recently offered in interchange.
We'll take one more question. And the way this question is phrased will suggest that they're not from North America. Is building wagons that last 40 years feasible considering economic instabilities in the world? Secondly, how would you monitor it if you still operate within 40 years if there was a body structure change in keeping the underframe of old design?
Well, again, of course, we're now talking 50 years rather than 40. But if a particular group of cars, let's say, starts to develop characteristic failures, there is a mechanism for requiring the car owners to pull those cars into a shop and make some appropriate repairs to them, reinforcements, whatever. So yes, it's difficult to predict what the operating environment is going to be 50 years from now, but the cars are typically designed and built with margins of safety, and but they are watched, and if particular groups of cars are observed to have unacceptably high rates of failure in one form or another, they are flagged, and there is a procedure for requiring that they be modified. And the same thing goes for components. And in some cases, if some components, a particular brand of roller bearings, let's say, or wheels made by a particular manufacturer are shown to fail frequently, they can be banned in interchange, and are. Okay, well, I want to thank you. And as a small token of our appreciation, a Railtech mug, which can be used with coffee or other beverages. Yes, well, we are talking about the railroad industry after all here, so. And the other thing I found that I want to give you is the interchange rules from 1963 when you graduated. Oh, very nice. From college. Yes, right. Bone up on that and see what's changed. Absolutely. Yeah, right. Yeah, I'll be interested in comparing it to my 1967 interchange rules, which I got when I started. Yeah, that's really neat, Chris. One of the things that I know we're going to find in here is that plain journal bearings were still accepted at this point, and the majority of the cars, and were being applied to new cars. Roller bearings were not required on new cars until 1967, I believe it was. So I very much appreciate that. You're quite welcome. Thank you very much. Thank you. Thank you, Chris.